Hello and welcome to our presentation on soccer game state reconstruction. My name is Emily and my teammates are Nelson and Tommy. Imagine you're watching a sports game on TV and you can obtain live statistics and a 2D minimap that offers further insight into the strategy and formation of your teams. That's what we'll be doing in our project. Soccer game state reconstruction is a computer vision task involving the tracking and identification of players from a single moving camera which pans left and right to keep the ball in frame, and constructs a 2D minimap of player and ball locations on a soccer pitch. This is novel and challenging because it's a very new and resource-heavy task. Our inspiration came from an industry challenge which only started this year, and the goal is to come up with a scalable architecture which can be used by everyone with solid accuracy. This is very powerful for the sports broadcasting industry as we can provide automated insights on team strategy and player movements to boost viewer engagement. The dataset that we use is from SoccerNet's 2024 GSR's dataset, which contains 30-second clips of games in 1080p, which was clipped into images at 25 frames per second. The annotations contain bounding boxes for each object in the image, labels for each object's type, jersey number, team, and coordinates on the 2D plane, and our goal is to predict each of these parameters. For each of the 3 Vs, because this is a new challenge with shifting industry standards, our goal is to create a framework that is simple and cheap, if not free to use, and we work to improve velocity by processing stages with GPU acceleration, veracity by measuring our 2D mappings against the ground truth, and we handle large volumes with frameworks such as GPT storage buckets, Hugging Face, and a GCP VM.
So this is an overview of our system. So for our test stack, we use Python to develop the whole software, and for frameworks, we use OpenCV for computer vision stuff and also supervision. And for models, we have 2 kind of models. So first is YOLO V5, which is used for object detection and tracking. And then TV CalLab is used for camera calibration. And for our architecture, we have been doing mostly the model training stuff on Google Colab to utilize the GPUs. And we also have a VM set up on Google Cloud Platform to run Airflow, basically, to perform all the tasks. And we also use storage buckets to store the input file and any intermediate files or the output files. And to break this further down, so this is an overview of our Airflow workflow. So users will start off by uploading a input video, a 30 seconds video clip to the Google Cloud bucket, and then it would trigger the Airflow manually. And then when Airflow start, it would transfer that input file from Google Cloud bucket to the Airflow's VM. And then you read the file and start doing tasks like detection, tracking, ball interpolation, key point detection, perspective transformation, or team assignment. So after all these tasks are finished, it will merge all the intermediate tracking files and use that file to analyze the pitch and the players and output an annotated video and a minimap video. And after that, it will combine the 2 videos to another combined video output. And then it will transfer all these output files back to the Google bucket so the user can download it.
All right. So to dive deeper into our pipeline, our first step is to detect the various objects that we want to see in the match video. These objects include players, goalkeepers, referees, and the ball. We use a YOLO V5 model to detect each of these objects and fine-tune them to specify the object classes that we want. In order to track these objects across frames, we use RoboFlow's supervision to assign tracklet IDs to each individual object, and that allows us to understand which player is which throughout the video. Next, we use linear interpolation to estimate ball positions between detections where the ball doesn't appear. This way, we have a constant estimation of where the ball is across the video as well.
Okay, for player team assignment, so we use k-means to do the clustering on the team color. So basically, there are two teams, and we analyze the frame and we assign each player to either team 1 or team 2 based on the colors on his jersey. So something like this. And for team 1 and team 2, instead of using the jersey color, we hard-coded two different very obvious colors to make sure the visualization is effective. And for the goalkeepers, it's kind of hard to just tell his team color just from his jersey. So we use another heuristic, which is to calculate the send choice of both teams on the pitch. And we pick the closer one's team color and assign that color to the goalkeeper.
Right. Now that we have all of the player detections and their coordinates on the 3D footage, we want to be able to map these locations onto a 2D plane. So to do this, we want to use a constant object which we can perform a transformation on, and this object is the pitch itself. How we define the pitch is by defining a few certain key points, such as the center circle, the corners of the pitch, the penalty spot as specific key points, and using a model, we can try to detect these key points on the current camera view and find a specific vector transformation, which is called a homography, to be able to map these coordinates onto the 2D pitch that we see on the right. Using this homography transformation and the player bounding boxes, we can then have coordinates that we can transform onto the 2D plane and visualize as dots as well.
And here's a quick demo of how the system works. So this is on Google Bucket. So now I'm uploading a input video to the Google Cloud Bucket. So right now I'm going to my Airflow page and open my DAG, and I will pass a file name to the flow and start the flow. So it reads that file from the bucket and start processing. And usually this process takes around 30 minutes to finish, but here I fast forward the process in the video. So you see the output is done. Then we go back to the bucket. We see some new outputs. And we see the combined videos. And we click that to download it. So that's the output from the system. And this is the full video. So we see each player is assigned to a team, and whoever is controlling the ball, it will be highlighted with deep blue color. And there's a triangle tracking the ball's position. And there's a minimap at the bottom to reflect the player's position on the pitch.
Okay, so due to time limitations, we are not able to complete all the work that we would have dreamed. But here are some examples of our next steps if we had more time. So first of all, to improve the tracking step, currently our tracklet assignment numbers are done arbitrarily based on the order of detection, but something that would be more informative is by assigning the detected jersey numbers and player names to each tracklet. And jersey number detection is a step that we also worked on, and we implemented using MMOCR. However, because the processing time was really long and detections were sparse, for example, when a player was facing towards the camera, we were not able to read the shirt number on their back. And so, because of these complications, we ended up not using this step in our Airflow DAG. To improve the perspective transformation, we would love to use some post-transform position smoothing, because as you might have seen in the output, the points had some wobbling and instability, and this is because we do our detections and transformations frame by frame, but optimally we would be able to use a full temporal analysis in order to identify a player between frames so that we can smooth out their position. But even without using temporal analysis, techniques such as Gaussian smoothing or the Kalman filter may be able to lower that instability a bit. For visualizations, there's many visualizations that can be produced, as well as sport-specific statistics such as heat map, speed estimator, or a Voronoi plot such as the one pictured here, which might show the territory that a player covers. And finally, our Airflow doesn't have its own backend at the moment, so we are unable to parallelize within the Airflow parameters, but that would be a future step. Thank you for listening to our presentation.